We continue with section 8.3, orthogonal projection and minimization. First of all, the vector spaces that we will consider will be inner product spaces, and it will be over the scalar field C or a subfield. The complex numbers, for example, the real numbers. And the inner product will be denoted as usual with this caret notation. Then we consider subspace W, subspace of V, and we define W perp, where we use this perpendicular sign or orthogonal sign, as a collection of all vectors V in V, such that W, let me first write that V is perpendicular to W for all W from the W subspace, which means we consider all the vectors that are orthogonal to all W vectors. And of course the orthogonality comes from the inner product to be equal to 0 for all W. It's easy to see that this W perp is a subspace of V. That will be probably a homework assignment or part of an exam. It's nice to see the subspace properties from the very first chapter we considered. Another property is that the W subspace and the W perp subspace has intersection which is just the 0 vector. If you go back to the definition of a direct sum, then you will see that that's all we need for the W perp to be equal to actually a direct sum, which means the representation is unique. Let me at least show this, that the intersection is the 0 vector. So if W is in W intersection W perp, then that means that W inner product W is 0. So that means the vector is perpendicular to itself. Or another way to say this is that the norm square of the vector is 0. Length is 0. And this is the case if and only if W is actually the 0 vector. So that shows that for all W vector in the intersection, W equals to 0. And that's exactly what the claim that W intersection W perp is just the 0 vector set means. So we use direct sums, W direct sum with W perp or any other subspace, when we wanted a unique representation in a vector space for all vector. This is clear that this is a subset or subspace of V. The question is, when is this equal to it? There are many cases like this, but we know in one case for sure. The next theorem says that if W subspace is finite dimensional, then this direct sum W perp is actually the whole space. This doesn't say that V has to be finite dimensional. It only says that W has to be finite dimensional. And it also doesn't say that if W is infinite dimensional, then it's not possible to have this property. It just says that if it's finite dimensional, then this property holds for sure. So the proof is based on the fact that if it's finite dimensional, then it has a W subspace has a basis with finitely many vectors. And so that's what finite dimensionality means. And then the Gram-Schmidt process creates an orthonormal basis, which is also finite. So let's denote this basis with D equals to V1, Vm vectors, and that's in W. Then for any V vector in the V vector space, we calculate AI to be the inner product of V with these VI vectors, and then set the linear combinations with AIs. So AI, VI, linear combination from 1 to M, which is, since all VI's are in W, that means this is also in W, so it's a W vector. Then what we do is, we did this trick before, that we recreate the V vector using this part of this. This is not necessarily the whole V, although this representation looks like the orthogonal vector representation that we used in the previous section. But note that this D is not necessarily a basis of the whole space, it's only the basis of the W subspace. So the trick we used before is that we set equal V to this sum, which is clearly not V. Something is missing, and what missing is we add it to get to it. Actually it's V minus the sum as I goes from 1 to M AI VI. So this is the W vector, and right now this is unique because of the basis representation VI. The question is what is this? So what we would like to see is that this is a perpendicular vector, which means is it in W perp? How do we see that? Well, we see that simply by taking the inner product of this vector with any U vector from W. So then this U vector can be written using the basis representation with these VJs, J going from 1 to M, where, as we saw before, so in W we have the D as a basis, orthonormal basis, so the coefficient vectors are U inner product Vj. And then we take the inner product of this vector, V minus the sum as I goes from 1 to M, AI Vi with U. So we write in the definition of the U vector, or the representation of the U vector. That's the V minus the summation AI Vi, and the U vector is the sum of Bj Vj. J goes from 1 to M. Then we use linearity in the first component, first argument. And we didn't use this much, but now we have to use the so-called sesquilinearity in the second argument, which means that these Bj multipliers can be brought out as a complex conjugate from inside the second argument. And also we can take it term by term. So we have, let's say we have V and this inner product, and we bring out the summation, we bring out the Bj with complex conjugate because it's from the second component. And then we are left with the V vector inner product with the Vj basis vector. So we are done with this yellow part. And then for the other part, we have a negative from the first argument. And when we multiply together, maybe first let me write out the summation. So we have the I summation there. And because it's in the first component, AI is brought out. And then from the second one, also the summation can be brought out, but not Bj. Bj conjugate is brought out. And then the Vi Vj inner product. Yeah, this two sums could be written into one sum with the double index notation. We don't really need this. We can leave it like this. Now, the point here is that according to the definition of AIs, that these are the inner products V with Vi. So these are actually just AIs. That means here we have the sum as J goes from 1 to M. This is J, now the index we are using. So this is Bj conjugate Aj. And because of the orthonormality, this is actually the Kronecker delta function, delta Ij. We only have the term where the I equals to J. There is a small mistake here. There is no vector for AI. AI is a scalar. So we have here, so the way I wrote this is that the sum, J sum is inside. Actually, in this case, it would be better to say that when J equals to I, then we have 1. And in other cases, it's 0. So the index could be from I, going from 1 to M. AI, and then from the sum of j's, bj's, only the ith one stays when the Kronecker delta is 1. But then, of course, the order of complex or real numbers multiplied together can be changed. Also, the index I or j, this is just a notation of running indices from 1 to m, so that doesn't matter. These are the same, subtracted from each other, we get the 0. So what this says is that v minus the sum I going from 1 to m ai vi has inner product that's 0 for all u in w. That means this is in w perp. And what we have is that in this case, then denoting this with w perp vector, we have that v can be written as w plus w perp. Now, if you look at the definition of w, that was unique, was from the inner product of v with vj's. So this is in w and this is unique. And then w perp was defined as v minus w, which means it's also unique. For all v element of the v vector space, v can be written as w plus w perp uniquely, which means exactly that v equals to the direct sum of w and w perp. That was the statement of the theorem. Note in chapter 4, we had that v was a direct sum of two subspaces, and then we had a projection onto w along u, which was a linear transformation from v into w. So we have now a similar situation, but we have a little bit better actually, because we have that one subspace is perpendicular to the other. The elements of one subspace are perpendicular to the elements of the other subspace. So in this case, we call this linear transformation an orthogonal projection. Definition: if v equals to w direct sum w perp, then p linear operator from v into v is an orthogonal projection of v onto w if we have two properties. P of w equals to w for all w vector from w subspace, and the second one is that p w perp equals to the 0 vector for all w perp vector from the w perp vector space. So this is definition. We can see that p is well defined. By this, what we mean is that if v is an element of the vector space v, which is the direct sum of w and w perp subspaces, then v equals to w plus w perp for some w from w space and w perps from w perp space. And these are unique, both vectors, w and w perp, unique to v. That's basically coming from the definition of the direct sum. And then if we apply the projection to this vector v, that means we apply it to the sum w plus w perp. P is a linear operation, so we can apply pw plus pw perp term by term. And then according to the definition 1 and 2, what we get is that this is simply w, which is unique to v. So that means for all v, pv is uniquely defined, and that's what we call well defined. It's also easy to see that we could have defined actually pv in this way, that pv is w, which is in the w space, where v equals to w plus w perp. And if you define it this way, it would turn out that this is the same projection that we had before. We also have several observations that we will not prove. We just write down because these are actually very simple and we already did this before. We had that p square equals p, which means it's idempotent. And compare this to observation 4.4.1. We also have that PV equals to V if and only if V is in W. What this actually means is that W is the image of P. And compare this to observation 4.4.1. Actually, these are all part of it. This was also in observation 4.4.1. And the next one is that P of V equals to the zero vector if and only if V is in the orthogonal W perp subspace, which means that this W perp is actually the null space of P. And again, see observation 4.4.1 for more details. Another observation is that I minus P is the unique orthogonal projection of V onto W perp, which just means that P plus I minus P equals to the identity operator, and compare this to observation 4.4.2. For the next one, we don't really have comparison as far as I remember, and this is that W is subset of, or subspace actually, of W perp perp. So this inclusion is actually true even if the sum of the subspaces W and W perp is not a direct sum. And that's because if W is a vector in W space, then for all U in W perp space, we have that W is orthogonal to U, but then by the definition of the double perp, so that's the orthogonal to the orthogonal subspace, that means that W is perpendicular to all W perp vector, so that means that W is in the W perp subspace, or the subspace perpendicular to the subspace perpendicular to W. So this shows part E. We have actually equality here, not just inclusion, if the sum is the direct sum. And this is the next theorem. If V equals to W direct sum W perp, then W actually equals to the W perp perp. So the proof of that one direction we have already. So this inclusion is actually E. All we have to show, so this is done. What we have to show is, for equality, is that we have the other type of inclusion. So we have that W perp perp is in W subspace. So using the P orthogonal projection of V onto W, what we have is that for all V vector from the vector space, we write V as PV plus V minus PV, and this is unique, and this is in W space, this is in W perp space, but then we have that according to E, that this is in W perp perp, which means that these two vectors are perpendicular, or with other words, we have that PV inner product with V minus PV is 0. So using this property, now we consider the V minus PV vector norm square, which is using the inner product, that's V minus PV inner product with V minus PV. Then we take the linearity of the first component, we separate this into V minus PV inner product and PV V minus PV inner product. But then what we have is that this cancels out according to this identity, and we are left then with V minus PV inner product. Instead of general v vector, we now consider a v vector in W perp perp, since that's what we have to show, that W perp perp is a subspace of W. So if you consider V from this W perp perp vector, if we have V in W perp perp, this vector here is, as we saw before, is in W perp. So that means that this equals to 0. Let me write this down separately. This V minus PV inner product equals to 0. But then this was the norm of V minus PV, the norm square. So this is 0. And that means V equals to PV, because this V minus PV must be the 0 vector. And PV is, by definition, is the orthogonal projection, so this is actually in W. So we obtained that W perp vectors are in W, which means that W perp is a subspace of W, and along with the E property on the first part, we have that W perp equals to W, which is the statement of the theorem. So we didn't have a formula so far for the orthogonal projection. If you look at this definition, it was defined as PW vector equals W vector, PW perp vector equals to 0. But then what we used before this definition is that we using a orthonormal basis in a subspace, we chose, using some vectors, we chose this expansion, linear combination, AIVI, that resulted in a W vector in W. So then in fact we have the formula for the orthonormal projection, which says that if we have orthonormal basis B with basis vectors E1, EM of W, then the orthogonal projection onto W of a V vector equals to the sum, as I goes from 1 to M, V inner product EI times EI. So this is formula for the orthonormal projection of V onto W subspace, using an orthonormal basis of W that we can always create. If W is finite dimensional, then we know that it exists, and it might exist also even if W is infinite dimensional. So the next theorem is the main theorem of this section, which is actually the minimization theorem, that says that suppose U is a finite dimensional subspace of the inner product space V, which is possibly infinite dimensional. We don't know that, and we don't have to know that. And if we have a vector V in the vector space V, then the V minus orthonormal projection onto U of the V vector norm is less than or equal to V minus U norm for all U vector in U. Furthermore, we also have that if U is in the U subspace and equality holds, then the U vector is actually the orthogonal projection of V onto U. So let's analyze this theorem and let's try to understand. First of all, note that V minus U norm, we didn't use this definition, but this is actually a distance between U and V. And you can even see that geometrically, the way we subtract vectors, so if this is V and this is U vector, then the difference is when you use the tips and roll a vector from the tip of U to the tip of V. So this is the U minus V. And if you look at, so typically we use the origin as the initial point for the vectors. And that means that using only the endpoints in this case, U minus V is the norm of U minus V, or the length of this is the distance between the 2 points, if we represent vectors with points. And then the picture is that we have a big V space, then it has finite dimensional U subspace in it. Then we have a vector V, and then if we check the distance between V and the U vectors for all U from the U subspace, so that means if we check this distance or this distance or this distance, all the different U vectors, U1, U2, and so on, then we get the shortest distance that's possible, which is, by the way, the definition of the distance between a point and a set. So the shortest distance is when we use the projection and the orthonormal projection of V onto the subspace U. So this gives us the minimum distance. V minus the orthogonal projection of V onto the subspace U is the shortest distance from V to the whole set U. The proof of this theorem, which has fantastic applications, I mean a lot of applications, so because we are in an inner product space, actually the proof is very elegant and short. Let U be a vector in the subspace U, then we have that the orthogonal projection of V is also in this subspace U. Then we have that V minus P orthogonal projection V is in the U perp. And then if we subtract these two vectors, both of them are in U, so we also have that P projection of V, orthogonal projection of V onto U minus U is in the U subspace. Then we consider the distance from V to the orthogonal projection of V onto U and the norm square. If we add to this norm square something else, which is the orthogonal projection of V minus U, so notice the difference between these two terms. This was V, this is U, but otherwise we have the orthogonal projections of V onto U. So we are adding something non-negative. That means that this is typically not equality, this is inequality, with the possibility of equality if this second term is 0. And then we use the fact that this is in U perp and this is in U. And then if we have orthogonal vectors, then we can use the Pythagorean theorem that says that the sum of the norm squares equals to the norm square of the sum. V minus PU V plus PU V minus U vector, norm square, and then of course these projections cancel out and we are left with the norm of V minus U square, which is exactly what the theorem says after taking the square root. Then it becomes just the length V minus P projection onto U of V norm is less than or equal to the norm of V minus U vectors. And then we have equality if and only if, going back, if and only if we have 0 second term there. So that means we have equality if and only if U equals to PUV. And that proves the theorem. There are many applications, and this is basically the basis of optimization.